Welcome to episode 4 of the week that was, and here is a quick walkthrough of 3 things: proving that interior angles of a triangle add up to 180 degrees, talking about our 5 reasons for triangle congruence, and then finally talking about rigid motions to prove superposition to prove triangles are congruent. So this is one proof that I need you to know how to do. Prove that all 3 angles in a triangle, the interior angles, add up to 180 degrees. So if you're given a triangle, or even if you're not given a triangle, we can call those angles 1, 2, and 3 in the triangle. And I want to prove that those all add up to 180 degrees. What else adds up to 180 degrees besides 3 angles in a triangle? A straight line. What I can do is take one of the sides and create a parallel line to that side, to that base. But make the parallel line go through the vertex on the opposite side. So I'm allowed to create another parallel line that goes through the top of that triangle, and I might as well just call those other angles something too. I'll call them angles 4 and angles 5. So this is an informal proof walking through why the angles inside all add up to 180 degrees. Well, one thing I know for sure is I know that angle 1 is congruent to angle 4 because those are alternate interior angles. And I've got parallel lines, so these angles have to be the same. I also know that angle 2 is the same as angle 5 because of the same reason. I also know that these 3 angles together form that blue line. So I know that angle 4 plus angle 3 plus angle 5 all have to add up to be 180 degrees. The reason I know that's true is because linear angles form 180 degrees. Linear angles, angles that form a straight line, linear angles add to 180 degrees. What I want is 1 plus 2 plus 3 equals 180. What I have is 4 plus 5 plus 3. I can replace a 4 with angle 1. I can replace, do I want to replace angle 3? No, because I want 1, 2, and 3 add up to 180. So I'll leave the 3 there. I can replace angle 5 with something. Angle 5 can be replaced with angle 2. And that proves that the 3 angles, 1, 2, and 3, must add up to 180 degrees. There are 5 abbreviations that we use to prove that 2 triangles are exactly the same size and exactly the same shape. I've got 2 pictures here that I'm going to add some details to. To be successful at this, what you want to do is mark the picture up with facts that you know are guaranteed to be true. In this picture here, I've got no facts at all. There's nothing that I know for sure. These look like right angles, but I can't say they're right angles. This looks like a midpoint, but they're not telling me anything about that particular point as being a special point. There's nothing that I can tell about these 2 triangles that have to be exactly matching or exactly equal to each other, except for one, and that's the fact that these 2 angles here are the same size. Those are called vertical angles. And vertical angles will always be congruent. Marking up your picture with decorations like these eyelashes right here can actually highlight. It's a great way to highlight what's actually true. So that would be the only fact that I would know is these 2 angles are congruent because those are vertical angles. In this picture below here, there's a lot of things that look congruent. These angles right at the dots look like they're the same size. This looks like it's an angle bisector, cutting this angle in half. But I don't know any of those facts as being true facts. Nothing is given to me here. The only thing that I do know in the picture is that these 2 sides here have to match up because both triangles are sharing this side right here. That's called the reflexive property. So there's no way to actually prove that these two triangles are congruent to each other unless I had more facts. So let me add some facts to the first picture. Suppose that I know that these two segments are perpendicular to each other. Perpendicular forms a right angle. Let's suppose that I also knew, they told me that these two segments were perpendicular to each other, and perpendicular forms a right angle. Since all right angles are equal to each other, I know those two angles are actually the same as well. That's still not enough evidence to prove that the triangles are congruent. I don't see any patterns there that I can use because so far all I'm sitting on are two angles. Oops, I thought that was blue. All I'm sitting on right now is that two angles match up here, and these vertical angles match up. It's not enough. So far in each triangle, I just have angle, angle. If I had one more fact, then I'd be able to finish it off. Suppose I knew that this segment here had a midpoint right here at point X. If X was the midpoint of this segment, I would know that these two sides are the same. And I could decorate that with maybe 4 slashes to prove that they actually are, to show that they're actually the same. If I had that pattern there, I just added on a side that matched a side here. Covering up one of those triangles is one way to actually determine which of the 5 reasons is being displayed. I got 2 angles in the side, so it could either be angle, angle, side, or angle, side, angle. Look where the side is. The side is not in between the 2 angles. This would be an example of angle, angle, side. For this design down here, if all I had are those 2 sides congruent, I can't prove that those 2 triangles are congruent. But if I had some extra facts, I'd be able to do so. So suppose that I knew that this angle here was the same as this angle here. So I'll decorate that with little eyeballs like that. Those 2 angles are the same. Suppose I knew that these angles here were also the same. Do I have enough information now to prove that these 2 triangles are identical to each other? Do I have one of these 5 reasons? I've got 2 angles matching with 2 angles and the side in between. Drawing on the picture is a great idea, and putting A's and S's next to the angles and sides that are matching up is a great way to actually see what's happening. So in each triangle I've got an angle, side, and an angle matching with each other. So now I have enough information to prove that those 2 triangles are congruent by angle, side, angle. Okay, and finally, talking about how rigid motions can actually get us to triangle congruency. So a rigid motion would be any of the following moves. Okay, a translation, which is a slide or a push. And when I slide or push this marker around, it does not change the size of the marker. It just changes where it is. That's an example of a rigid motion. Another rigid motion is a rotation. If I rotate the marker, it keeps the size and shape the same. And a third transformation would be a reflection, which would also keep the size and shape of the marker the same. So any way I slide the marker, rotate the marker, or reflect it, the marker is staying the same size and shape. That is called a rigid motion. What is not a rigid motion is actually dilating the marker, making it smaller or making it larger. Okay, and that's coming up in a future chapter. So the rigid motions are translation, reflection, and rotation. We use those rigid motions to establish something called superposition, which is piling up one shape on top of the other. I know that my hands are actually congruent to each other because I can actually take them and place them one on top of the other. It's called superposition. So one thing that gets brought up in this chapter is talking about how do I get these two shapes to be in superposition? What kind of rigid motion would I use to get these two handprints on top of each other? Well, in this case, I could slide one hand up to meet the other by the tips of the thumbs and then reflect to get the two hands in superposition. If I had something like this, where I was trying to get the handprints on top of each other, I'd have to do a few moves to get there. I'd have to slide or translate to get the fingertips together. And then I could rotate that hand. See me? I could rotate that hand together to get those thumbs to touch and then reflect to get them in superposition. And that's as tricky as it can be, is where you need three rigid motions to actually get them to line up one on top of the other. These are a lot simpler. For these two triangles here, these two triangles are congruent to each other because of side angle side. I could also prove that they're congruent to each other by doing a rigid motion. I could flip one triangle onto the other, and a flip is called a reflection. So for this particular example, I could just say that I can reflect over the line segment XY. I could reflect triangle WYX so that W lands on top of Z, Y lands on top of Y, and X lands on top of X. So I would just fold over like that to bring the two triangles into superposition. And that proves that the triangles are congruent. It's an informal way of showing so. So here's another example. These two triangles are congruent because of side, side, side. I also know they're congruent because I can take this first triangle and translate it or slide it down here to place it in superposition on top of the other. So if this had a name like triangle ABC, and this had a name DEF, I could say that my move or my rigid motion would be to slide this entire triangle down on top of this one by following this vector, this directed line segment from A to D. That's what I would have to do to slide this onto here. The way we write it would be to say it's a translation or a slide, and sliding down from A to D. So we write ray AD, and what do we slide? We're sliding the entire triangle ABC. All right, last but not least, this example here, these two triangles are going to be congruent to each other because I've got two sides that are the same, the side in the middle that's the same with the reflexive property, and I also have, because these are parallel, that's what those arrows mean, I also know that these two angles are the same too. So I have a side angle side pattern in both triangles, and that's the reason why those triangles are congruent. I can also prove that those triangles are congruent by using a rigid transformation. So can I get a reflection to turn this triangle into that? A lot of students think so. A lot of people would say so, that I could reflect this triangle to become this triangle. If I reflect over that line in the middle, though, I do not have, or that shared side, I do not have the triangles in superposition. Point M, when I reflect, would not reflect onto point O, but reflect down here. So another rigid motion could be used to get these triangles in superposition, and that would be a rotation. I could rotate on the midpoint 180 degrees, and that would bring the triangle on top onto the triangle on the bottom into superposition.